Hey ladies, so today we're working on section 8.4, so we're going to be looking at logarithmic functions and exponential functions. So last section we looked at some laws dealing with logarithmic, and we even kind of included some exponential functions there. And so now what we're doing is we have these statements, and they're basically going to be like these laws here, and we're going to apply these statements, and they're going to help us to solve both logarithmic functions and exponential functions, okay? So to start, suppose we were given, we have two logarithmic functions. Suppose we had log base c of L and log base c of R, where L and R are greater than 0. So remember we kind of talked a little bit about why these values here have to be greater than 0. So they can't be 0 or a negative number. And also the fact that we also can't have c is less than, or sorry, it's not equal to 1. Okay? So from here, say we have these two logarithmic functions. So if we have the log of base c, L, is equal to log base c, R, so they have that same base and they're equal to one another, then L is equal to R. So it's important here we have the same base and they're equal to one another, so then that means that L and R have to be equal then, okay? So then looking at our second statement, we have the equation log base c, L, is equal to R, and we can rewrite this as logarithms on both sides. So what we'd have is log of base c, L, is equal to log of base c, c to the R. So to help you see this, let's look at, suppose we just looked at this log function here. So say we had log of base c, c to the R, and let's just let that be equal to x, just for our example, okay? So if we wrote this into exponential form, we'd have c to the x is equal to c to the r. From this, we can say that x is equal to r. So if x is equal to r, we can substitute r in for x and say that log of base c, c to the r, is equal to r, which is that right there, okay? So r is in fact equal to log base c, c to the r. Okay, so looking at that third statement there, we have the equation log base CL is equal to R. This we can also rewrite in exponential form as L is equal to C to the power of R. So it's going to go along the same lines, or it's going to be pretty similar to as an explanation as what we did in example number, or in our second statement. Just this time, instead of rewriting our log function, or I guess our right-hand side, we're going to rewrite that left-hand side as exponential form. We'd find that L is equal to C to the R. You guys can try that one out. Looking at that last statement there, we have the logarithm of 0 or a negative number is undefined, which we already know that. And so to define or identify whether or not we have an extraneous root, and if you guys remember what that means is that the solution doesn't work or doesn't hold true. So to do that, you would substitute that value or the root that you found into that original equation and check whether or not all of the logarithms are defined, and whether, and if we're given an equal sign, whether the left side is equal to the right side, okay? And just one last note here, so I gave you guys a couple of stars here. It's a bit of an important note. So generally, when we're trying to simplify some expressions like this one that we have below here, what we're going to do first is we're going to use those laws from 8.3 first to simplify, and then we're going to use these statements here to finish it, okay? So let's scroll on down here. And I'm just going to quickly erase some of my scribbles here. We don't need that anymore. Alright, so for this first example, we have the log 5x minus log x minus 1 is equal to 1. So using our rules from, or laws from 8.3, we have a subtracting symbol there, or a subtraction symbol. So that means that we're going to be using our quotient rule. So here we have 5x would be m, x minus 1 would be n, and what we can rewrite our left-hand side as would be log 5x divided by x minus 1 is equal to 1. From there, using our statements, we know that, if I'm just going to scroll on up here, we can use our third statement here and say that if we have a log base c, L, is equal to R, then we can rewrite that as L is equal to c to the r. So we're going to take this, so we'll have 5x over x minus 1 is equal to the base, which when it's not given, remember that means it's 10. So we have 10 to the 1. Then what we can do is simplify, so we have 5x over x minus 1 is equal to 10. And then to get rid of that fraction, we're going to multiply both sides by that denominator. So we have 5x is equal to 10 times x minus 1. And from there, what we're going to do is we're going to distribute this 10 to each of those terms in that in those brackets. So we have 5x is equal to 10x minus 10. So now this is probably starting to look more like grade 9 where we're solving for a variable, and that's exactly what we're going to do. We're going to move each term, we're going to move all the x terms to one side, all the numbers to the other side, and then solve for x. So we'll move 5 over to the right hand side, and we'll move 10 to the left hand side. So to move 10, we'll add, so we'll have 10x, or sorry, just 10, is equal to 10x minus 5x is 5x. And then finally, to get rid of x, we're going to divide both sides by 5. So we have x is equal to 2. So now that we've solved for x here, what we can do now is we need to verify this. So our first step, we can do this in two different steps. Our first step is to define the restrictions. So as long as it fits in those restrictions, things seem to be going all right. But then one thing that you also need to do is double check by verifying it. So plug it back into that original equation. I'm just going to scroll on down here. So we're going to first find our restrictions. Okay, so from here, our restrictions, remember we're just going to be looking at this m and n term, those ones cannot be equal to 0 or be a negative number. So what we're going to do first is, normally when you find any restrictions, we set those terms equal to 0. So we'd have 5x is equal to 0, and we also have x minus 1 is equal to 0. So when we solve, we're going to divide each side by 5, so we have x is equal to 0. And here, for this term here, we're going to add 1 to each side, so we have x is equal to 1. So at these points here, this is when your log function is equal to 0. So remember, it can't be equal to 0 and it can't be less than 0. So one thing that we also can do is we're going to further simplify our restrictions by saying x cannot be equal to 0 and x cannot be equal to 1. We can further simplify this one more step. What happens if we put, say, 0 into our second term, into our second log function? We'd have a log of negative 1. So actually what happens is that, what needs to happen is that it needs to satisfy both of those restrictions, or whatever our restriction is, it has to satisfy both of those. So you go with your bigger value, and so that means that x must be greater than 1. So if we went with a value in between these two restrictions, that wouldn't work for our second log function. So that is why we exclude this smaller restriction. So it has to be that bigger restriction, and what you can do is take test points in between each one, or either above and below. So take one, so one that's above this, so you can try testing 2. Would 2 make this true? What about 0.5? Would that make this true? And you would see that for our second log function, that wouldn't be true. Then we could also check maybe below x is equal to 0, so try negative 1, and you would see that for actually both of those, it doesn't work. So make sure that you pick your biggest, or I guess it'd be the bigger restriction. That also depends on what you're given, but in this case here, it is x cannot be equal to 1, and then you would write that as x must be greater than 1. You can even choose a test point, and then hopefully that should work. So from here, you can compare, is x equal to 2? Does that meet your restriction of x must be greater than 1? And that one, it does. 2 is greater than 1. So from here we can do a check, so let's verify. Substitute in 2 in for x. So we have the log of 5 times 2 minus the log of 2 minus 1, and that should be equal to 1. So let's simplify this. We have the log of 10 minus the log of 1. That should be equal to 1. Looking at each of these individually, if you look at log of 10, that is the same as saying 10 to the x is equal to 10. So this one here is your x is equal to 1. Looking at the log of 1, that is saying 10 to the x is equal to 1. And here what would satisfy that would be 0. So we'd have log of 10, which would be 1, minus log of 1, which is 0, should be equal to 1. And what we find there is that 1 is in fact equal to 1. So x equals 2 actually checks out, so that means that x is equal to 2 is a solution for that first example there. Okay? So now let's move on to example number 2. So we're going to do the same thing. We're going to simplify using our rules from 8.3. Then we'll simplify it further using those statements if we can. And then what we're going to do is we'll verify it by checking the restrictions and actually substituting it into that equation. So now I'm going to erase all my scribbles so we can move on to number 2. Alright, so here for number 2 we have the log of base 6, x minus 3, plus log base 6, x plus 6 is equal to 2. So we're going to use our 8.3 rules, and if you guys notice here, we have a plus sign, or we're adding. So if you guys remember that law, that is the product law. So we're going to be writing this as two values multiplied together. So here is m is equal to x minus 3, and n is x plus 6. So what we have is, using our product law, we have log of 6 m times n, so we'd have x minus 3 times x plus 6 is equal to 2. From there, what we can do is we can simplify these two, brackets there. So what we'll have there is log of base 6, then we'll FOIL, so you do x squared, we'll put this in brackets, then you'll do x times 6, so it'll be plus 6x, you'll do negative 3 times x, negative 3x, and negative 3 times 6 is negative 18. That's all equal to 2. So now let's simplify this right here, and we have log of base 6 x squared plus 3x minus 18 is equal to 2. From here, what we're going to do is you can use your statements, but one thing that this actually looks very nicely, or something that's very nice about, is that we're going to write this into exponential form, and you'll see why I do this. So we have b e n, so we'll rewrite that as 6 squared is equal to x squared plus 3x minus 18. Now we're going to move everything onto one side. So we can also simplify this at the same time there. So we have 0 is equal to x squared plus 3x, and this is 36. And to move that to the other side, we'll subtract. So it'll be negative 18 minus 36, and that will be equal to negative 54. Now from here, what we're going to do is we're going to factor, but we are getting close to our 15-minute mark there, ladies. So what we're going to do is factor this one on your own there, and check the solution in the next video, okay? So try factoring, see what you get, and even if you want to, go ahead and check your values, and you might be surprised to see that maybe one or maybe both might not work. But you'll never know until you check it out. So move on over to video number 2 when you've tried this out on your own.